Okay, let's look at this AP problem. It says that you have a piecewise function. Part A says, for what values of can P will f be continuous and differentiable at x equals 1? So let's start with the continuous piece. If you have a piecewise function and you want it to be continuous, they have to connect. So that means the two pieces have to be equal to each other. So I'm going to set these equal to each other, and it says you want it to connect at x equals 1, so if I plug in 1 here for x, I get 1 equals k plus p. Okay? Now, I have two variables, so I know I need another equation, but it also tells me that this function is differentiable. What that means is that this is a smooth, continuous curve. So in order for the slope to be smooth when it connects, the pieces by themselves are differentiable because it's a polynomial. It means the derivatives have to be equal. So I'm going to take the derivatives and set them equal to each other. Okay? And again, same thing. I'm going to plug in 1 for x, and if I do that, I end up this. So notice I can find the k pretty easily and plug the k back in here, and then we can figure out that p is 2. So there's my k and my p. Okay? Part B. For what values of k and p found in part A, so use these numbers and plug it into your equation now. So this is my equation. 2x minus x squared for x is less than or equal to 1, x squared, k is minus 2x, and p is 2, or x is greater than 1. It wants to know where f is increasing. So when you see these words increasing, you should be thinking about f prime. So it's a piecewise function, so I'm going to take the derivative, but I'm just going to do the two pieces separately. So the derivative of the first piece is 2 minus 2x, and the derivative of the second piece is 2x minus 2. Now let's think about what the sign of these pieces are. This piece I own is this derivative, but we're only looking at the values when x is less than or equal to 1. So if I plug in any number less than 1, this is always going to be positive. So this is positive for all values of x, if x is less than or equal to 1. This upside capital A means for all values. So for any x value less than or equal to 1, it's going to be positive. And it's okay that exactly 1, that only that one endpoint it's at 0. Okay, that's not important. This derivative, when I plug in any number greater than 1, this is also always positive for all values of x when x is greater than 1. So the two pieces, the derivatives, will always be positive on the interval that I'm looking at. So f prime is always positive, so f is increasing everywhere on this graph. Okay. Lastly, part C. Use the values of k and p found in part A again, and this time find your points of inflection. So when they talk about points of inflection, you should be thinking the second derivative. So I'm going to do the exact same thing. Second derivative of this is negative 2 when x is less than 1, positive 2 when x is greater than 1. Second derivative goes from negative 2 to positive 2 at 1, so there is a point of inflection. F double prime changes from negative to positive at x equals 1. It did ask for the point, so you do want the ordered pair. So 1, 1 is a point of inflection.